Alright, welcome to another Draft Science. DraftPhysics.com on the internet. DebatePhysics.com also. A video presentation. Alright, this is part 3 of photons. And I guess there's 2 parts to this part. 2 things to emphasize, I suppose, as additions to what has previously been stated in explaining how photons actually interact with matter, and I will try to do that in as concise and with as few words as possible, but actually saying something that matters. So photons hit a surface, and the idea is this: they're, physics says they hit electrons, and that's true, but it's not entirely. It's not the whole truth. Gotta fix that. There, it fixed itself. Light went out. So yes, there's a bunch of atoms on a surface, and the truth is we see photons either by them being reflected or them causing electricity. So you sort of have to understand what electricity is before you can understand what a photon is, because there's such a connection between photons and making electricity. And so solar panels and the whole thing are all based on that kind of idea that you can convert light, the momentum of the light, into electricity and then collect the electricity. So I would argue that electricity is atoms just being polarized. So atoms are sitting in a surface, and basically, you can't see that, they would all be neutral. They all want to stay the same balance, you could argue. And when you introduce something to create electricity, either through a conductor or by adding something less direct than actually adding electricity, is the fact that they will share this change. So if you change the first atom by adding an electron, the next atom will share that change, and the next atom will share with that atom. And so in a sense they will all attempt, there's something like this, the size difference. You could even see it as a size. It's probably a shape difference, but whatever. And they'll try to share it, so they all just add a little bit in the end to who they are, because they're going to share it with all the connected atoms. And so the idea of you hitting one atom with a photon isn't realistic, in the sense that it isn't going to duplicate electricity, because one single photon won't have enough energy to do that. But if you hit the surface with more than one, then that sharing process will automatically take care of the argument. So you could argue that, okay, the photon is made of elemental bits. Let's just say there's 4. Let's just say there's 3 for the sake of argument. That if you get hit by this much, you'll get, and at a frequency, that'll constitute something that could register as a something that creates electricity, or something that creates a stimulus in your eye. And without that much energy, you won't see anything. Could be the argument. So what's really happening is, as stated before, there is a polarization that the light has. That is, they're a little bit out of sequence in their movement in this direction. And you could argue that when they hit a surface, what are they going to do? Well, I would argue that it's like you throwing rocks into a pond in a sequence. The first one creates a change in all the atoms next to it. So this atom you hit with one of these little pieces, it expands, let's say. You can see that? Well, you can almost see that. My truth speak is in the way. Anyway, somebody's got to tell the truth. So it's a little bigger than the other atoms, I'm just saying. So it's almost like it's a wave. So if it was water, a pond, and you threw a rock, the first rock makes a ripple. Okay, and all the other rocks start all the rest of the water starts rippling in sequence, and it gets dimmer and dimmer as it gets further away, weaker and weaker. And so then the next rock hits, and the idea is it's hitting behind a wave. And now it's going to push that wave with more velocity. It's going to be a bigger wave. and then your next rock. So you threw them in a sequence, a frequency. Alright, so the first one hits, the second one hits further out, it hits further away, it hits behind the pushing of the electron. So let's just understand, this has an extra electron. Basically this is a pushing of electron force. You're pushing one electron against another electron against another electron. Now you hit behind where you've pushed an electron, you're going to push that electron a little faster. And then it's going to do its waving, and then you're going to hit it once more a little faster. So now you're giving the momentum to an electron. So yeah, all these other electrons are also moving, but they're not going to get pushed. The only one that's going to get pushed is the one where your rock landed behind it, and the third one behind where it gets hit. So that's the polarization part. There's only one vector that gets the extra energy. The rest of the vectors just die. So the higher the frequency, obviously the stronger the electron is slowing down. So the electron pressure starts off high and it gets lower and lower as it goes further away because it's getting diluted. So the higher the frequency, that is the quicker you throw the rocks, the less time it has to slow down, keeping its peak velocity. And so when you're adding the velocity, you're adding it to more existing velocity. That's why the the photoelectric chart looks like 0, and then all of a sudden when you get to a certain frequency it does that. And it does this linear thing. The faster you throw the rocks, the more you add. So there's a certain minimum you have to be at. Alright, so if you're throwing the rocks too slow, these waves all got way too weak. You can't add any extra energy, and you're out of luck. You're not going to get enough energy to eject the electron. But if you throw it fast, the rocks fast enough, you will add enough energy, and that's when you start the game. And the faster you throw the rocks, the less energy the system loses. The system has time to lose, and therefore the more energy you're going to give the electron. So it's that simple. The faster you throw the rocks, the less energy the system loses. So you're hitting a system. So you're hitting more than one atom. So just like you could argue an antenna, okay, producing a radio signal, a radio photon. The idea is that it's really just about the speed of light, how fast the electricity can get up the wire, okay, and change the atoms, because that's creating the signal. And so that's going to decide, you know, how big how big, you know, how large the wave is going to be how fast, how much electricity can get through in the amount of bang you're giving it. So you're turning this on and off, this electricity at a frequency. Okay, and the higher the frequency you're turning it on and off, the further, you know, the pieces of the antenna are getting excited by that amount of electricity traveling at the speed of light. And that'll tell you how far it can get in that tiny amount of time. So the less the time, the less height it can get up the antenna, and that's why you need shorter and shorter antennas for higher and higher frequencies. And that's why you need long antennas for high frequencies, is because you can't you're giving the electricity plenty of time to travel much further up the antenna and produce more electrical effect. But it really can't create any electrical effect with extra antenna. Extra antenna isn't going to do it any good if you're on and offing. This is just will be noise. This extra antenna will just create what's, you know, a kind of noise, because the only part that's creating the signal is the part that's exactly connected to the ons and the offs. Anyway, so the whole point is the point of me bringing up how photons are created is that it's more than one atom that creates a photon, and it's certainly more than one atom that receives a photon. Now, the other important fact, so just to understand it, it's not merely a photon. You know, when they draw these pictures of an atom and they have this little squiggly photon come popping out of the atom from an electron, it's only a piece of the energy. Oh, damn that light. Oh crap, I was paused all this time. Damn. Oh, I made so many good points. Ugh. Alright, I have to figure out where I was. Alright, well, anyway, I just did 40 minutes of video that, not recorded. I hate when that happens. Alright, because it's never better the second time, frankly. Alright, so he's talking about the energy needed to remove a photon from the surface. He says lots of stuff. I drew a picture explaining. I guess I'll just have to do all that crap over again.
E equal to W, which is called the work function.
So you can't take the word work seriously when they say it because it doesn't mean anything. It's just momentum. All right, so we're gonna. I'll do this first because there's just no point. Oh, this is so irritating. Anyway, so I was trying to make the point that all right, these are little bits, and the whole photon doesn't hit a single atom. So that's just not the game. A piece of the energy hits an atom. And the free electrons are not free. So anywhere, if an electron's anywhere in space, it's going to go somewhere. I throw an electron anywhere, it's going somewhere. Because there's always some place that looks more positive than negative. There's always some place that looks like it has more electrons it wants to run away from. There's some place that always looks like a keyhole or a place to go, and that's where it's going to go. It's always going to be pushed more from one side than the other side by the density of the forces. It's always going to look. Let's say the electron is attracted to blue. The purple is always going to be a little bluer someplace and redder in other places. And it's always going to go where it's bluer. Alright, so you can't really see the colors on this because of whatever reason. Okay, so I should increase the saturation. So we just put X's. These are the electrons. So this is what an atom looks like. So obviously if I'm looking from here, it looks positive. Alright, if I'm looking here, it looks negative, right? My hand's in front of my face. You can't even see it, okay? There's no positive at all. But the closer the electron gets to the proton, the nucleus, okay, then all of a sudden the nucleus is visible, more visible. So it's just about proximity to these things. So the idea of this free electron, it's not really free. It sees this atom, it's over here flying through space, and it sees this positive. But unfortunately, when it gets about here, what's it going to see? It's going to see this electron, it's going to see this electron, and it's going to put on the brakes. So even though it wants to go here, it just can't, because to go there, it has to get too close to this electron. The repulsive pressure from the electron is now stronger than the attractive to the proton, so it's stuck here. It's stuck. But it's not stuck very strong. So this is the free electron, okay? It's not really free. It's not moving all over the surface, bouncing about. It's found a home. It's just not a very strong or reliable home because it's stuck between two equal forces. So all I have to do is give it a little bit of a kick and it's gone. It's back looking for a new home. That kind of idea. And so you can understand that if I push on it this way, if I hit it and I push it closer to these electrons are going to push on each other and the whole atom is going to expand, okay? And if it's sharing an electron with another atom up here, you can see that that atom is going to be affected. All the atoms are going to be affected. You push on one electron, you basically push on all the electrons. That's sort of the nature of the atomic structure of a material. So that's what I mean by sharing. You poke it here with one bit, then over here it's going to get poked with another bit, and that pressure is going to increase because you're adding more pushing pressure. And the eventual outcome is going to be that you're going to create enough tension, and when everything contracts back again, it's going to eject the electron with enough energy to, shoot it across. Shoot it. How far it can go, well, that's under debate. Can't go very far because it's going to get dragged to a halt because it's going to be moving into more force and absorbing its energy, the momentum of that force. But anyway, so okay, so I just wanted to throw that in. It's probably something else missing, but whatever. I'll just have to accept the losses. Sorry. You won't know the losses because you won't be able to make the comparison between the first video and this one. But the first one was really good. Anyway.
So how are you going to get an electron to acquire some energy? We all know electron is an electric charge. I have to apply an electric field. And I know electromagnetic waves are nothing but electric and magnetic fields.
So this is all nonsense. There's no field. The field is the photon. That's Einstein's whole point. The field is actually made out of something physical. So as much as Einstein's guilty of creating fake fields for gravity, he liked real fields for the electric field and the magnetic field. He didn't like this idea that there's some magical field that does magical things, and certainly didn't like the idea that it's doing it based on some probability math.
So I shine a light, source of light, towards this. The electric field comes and grabs the electron and shakes it loose. Hopefully it'll shake it loose from the metal, giving it enough energy to escape, and once it escapes, it can take off.
Right, so the simple explanation is it goes in, and the idea is the faster you hit it with more energy, the more none of these other electrons slow down. So the other electrons, as you hit it, the electron's going to slow down. So as soon as you hit it, it starts slowing down. It's going to get dragged to a halt. It's in a bunch of pressure. It's got a bunch of things pulling on it. It's going to stop moving. So the idea is you're going to create a movement that you know has a dampening effect. You know the system is going to dampen that motion. So as all the electrons move, the amount of energy in each one gets smaller and smaller and smaller. So it's dampening all the energy. And the simple equation is if you can put your energy in, you're going to hit it 3 times. If you put your energy in slow, okay, then all of the energy got dampened out of it because you put it in too slow. But if you put it in fast before it can dampen, then the system will keep more of the energy. So the faster you can hit it, the more of that energy stays as coherent for that amount of time. So it's at a higher velocity. So essentially you're just saying you've got a cart and it slows down. You push it and it rolls 5 feet and it stops. Well, if you push it and allow it to roll 5 feet and stop, and then push it again and roll 5 feet and stop, and push it again and roll 5 feet and stop, obviously it's not going to gain any real velocity. It's not going to ever get more than that single amount of velocity of the push. But if you can push it sooner than 5 seconds, right? So 3-second interval, then it's still moving when you're pushing it again. So that's the increase in the velocity. And obviously if you push them all like so fast that it's almost one push, then you get the full 15 miles an hour. So instead of 5 miles an hour, you can have 15 miles an hour if you push fast enough. If you throw X-rays, you throw, gamma rays.
So they took some light source and they aimed it at the metal. See if electrons come out. They didn't. So what do you think you will do to get some action? Yes? So you make it brighter. You say, okay, let me crank up. That's what anybody would do, crank.
Right, so this isn't history. This isn't the story of how they did it or any crap. So this isn't how it was discovered. But the simple argument is that's actually what he's saying here isn't true, right? So in the sense that increasing the amount of photons will, if you do enough of them, if you hit it with a laser beam, then what you'll do is you'll get an improbable event, events that don't happen too often, where one photon hits exactly the same place as another photon. And so you're taking 2 frequencies that are too slow, 3-second intervals, and you're overlapping them. And now you have 1.5-second intervals. So you've increased the frequency of the event by overlapping 2 photons. So if you can increase the amount of photons, then you can increase the probability or the possibility of incidental photons being in the same general location, hitting the same place. And if they sit exactly the same place and exactly out of phase, then they will be able to produce this effect. So it's just a minor, but it's such a minor amount that it doesn't really significant. But you have to just say it is true, that you can increase the intensity and create a few electrons that will leave the surface. But it's far more effective to just increase the frequency of the light.
The intensity of light. Make it brighter and brighter and brighter, nothing happened. Then by accident, they found out that instead of cranking up the brightness of the light, if you cranked up the frequency of light slowly, suddenly, beyond some frequency, you start getting electrons escaping the metal. So here's a graph you get. Here is the...
I mean, it was just kind of obvious. Obviously, they said, well, we shine visible light, we don't get much. We shine ultraviolet light, we get a lot. So that's the easy answer.
Let me just plot, if you like, h bar times the omega. In those days, they didn't know too much about h bar. You can even plot omega, it doesn't matter. And you plot here the kinetic energy of the emitted electron. And what you find is that below some minimum value, no electrons come out. There's nothing to plot. And once you cross...
So that's just going too slow. You're putting the energy in, and the drag, the system's drag, is pulling all the energy out before you put new energy in. So you're just defeating your purpose because you're not putting the energy in fast enough to overcome the drag effect, the fact that the whole system is going to be dampened out of energy.
The magical omega, and anything higher than that, you get a kinetic energy that's linear in omega.
So it'll just, you want to double the amount of stuff, you just double the frequency. So it's just basically saying you're just going to change the velocity. So now you're going faster than the system's drag. And if you push the energy in faster than the system's drag, every bit of speed you increase is time. So you're basically just defeating the system's dampening effect, the effect of the system to pull all to use up the energy. You're going so fast that you're defeating its capacity to do that, and so that's why you get a linear increase. The faster you put the energy in, the more energy is kept by the electrons.
Now, the kinetic energy is the energy you gave to the electron minus W. Energy given to the electron minus W, because you pay W to get it out of the well, and whatever is left is a kinetic energy.
So here, they're basically confusing the work function with an amount of energy when it's really about the amount of time. And all you're doing is you're finding a trick. You're putting the same energy in, the same number of little things are hitting, the same number of rocks. You're throwing them, and you're throwing them exactly the same speed. All you're doing is throwing them in a shorter and shorter amount of time. And so you're defeating the system's capacity to dampen the energy out, and that's it. So the quicker you can throw the free rocks, the more effect they can have on the electron, because the system won't steal the velocity from the electron.
So Einstein had predicted photons from independent arguments, and according to him, light at frequency omega is made up of particles, each of which contains energy h bar omega. So you can see what's happening. If you got low frequency light, you're sending millions of photons. Each carries an energy h bar omega somewhere.
So again, let's just always remember, when we say it's photon, it's not there's not a thing. The thing isn't the photon. The photon is the composite object. It is the pattern. So the pattern, dot, 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 4 little bits of energy, that's the photon. I can have the bits far apart. I can have the bits close together. High frequency, lots of capacity to do work because the work won't be dragged to nothing. Low frequency, high probability that the work won't be noticed because it will all just get consumed by expansions of atoms.
And here, none of them has the energy to lift the electron out of the metal. Like sending a million little kids to lift something, and they cannot do it. Okay? They cannot do it, but if you send 10...
So again, it's not a logical argument. Obviously, the one atom going 1,000 miles an hour has the same energy as the 1,000 atoms going 1 mile an hour. So little kids could do it. He just didn't. He didn't do that experiment, frankly. Obviously, little kids could do it. They all together, a whole bunch of little kids will lift the same amount as, one giant big person.
Tall, powerful people, they will lift it up. So what's happening with light is that as you crank...
So he's misunderstanding. He's thinking there's more energy, and there's not more energy. There's just energy delivered over a shorter period of time. Period. Simple. Ultraviolet light doesn't contain more energy. It's just going to deliver the energy in a shorter amount of time. And time is critical when you're hitting a substance that will dilute the energy. If you give it a chance to dilute the energy, it will. If you don't give it a chance to dilute it, it won't. It's that simple.
Back up the omega, even if it's not very bright, the individual packets are carrying more and more energy and more momentum. That's why they say.
So they don't have more momentum, they don't have more mass, and they don't have more velocity. So we can, if they took the word momentum seriously, they really don't think it's a serious word. They don't have to pay any attention to the mass and velocity part. They can pretend the photon has a massless particle, but it still has momentum. I mean, it makes no sense at all. But it has the same momentum. And again, it's just about the system. The system is changing it. The atoms, the fact that the electrons in the substance are going to share the energy, that's the part you have to defeat. That's the variable you need to crank down to increase the effect. You're going to increase the effect by breaking the dampening of the electron system, defeating it. It's a trick. There isn't more energy. There's just energy applied more efficiently.
Succeed in knocking the electron out. And in fact, if you said the energy of each photon is h bar omega, then the kinetic energy of the electron is the energy you gave with one photon. Take away the W, that's the price you pay to leave the metal. That's of its kinetic energy.
Right, so it won't be one photon. You can't, I mean, one electron isn't going to be, it's going to be an exchange of energy with atoms, numerous atoms, and it's the numerous atoms that are going to eject one electron.
So when plotted as a function of omega, K should look like a straight line.
What the hell
with
did I
intersect
do
W.
there?
And that's what you find.
I don't need that.
It's one way to measure the work function. How much energy do we need to rip an electron out of a metal depends on the metal. And you shine light and you crank up the frequency.
Right, so it just has to do with, you can understand that the dampening effect has to do with how dense the atoms are and how close they are and how small they are. So the size of the atoms will decide how quickly the energy is dampened out of the system, how quickly jolting one electron jolts the other electron. So different metals will have a different density, and that density is going to decide how long it takes for the energy to be dampened, and so you're just defeating the dampening with different metals with different amounts of time. You have more time with some metals and less time with other metals. Some metals will require you to put in higher intensity light, higher frequency light, because they dampen much quicker, and then other metals will allow you to have lower frequency light because they dampen much slower.
Till something happens. And just to be sure, you go a little beyond that and you find that the kinetic energy goes linearly in omega. Anyway, this is how one confirmed the existence, indirect existence of photons. There's another experiment.
So again, this is just one way. Obviously, I think the surfaces in the double slit experiment, understanding that the surfaces are causing the effect, they're completely mathematically in control of the effect, recognizing them as the point sources of the energy that causes the fringes, clearly is pretty particle proofy. So instead of being nail in the coffin evidence for waves, it's nail in the coffin evidence for particles.
That also confirmed the existence of photons. Look, that's the beauty. Once you got the right answer, everything is going to be on your side.
So it's so funny once you have the right answer. So they have bent space, they have magical electric field, magical magnetic field, magical dark matter, magical dark energy, magical antiparticles. I mean, it's all made out of magic. And they talk about having a right answer. And none of it's physical. Bent space, non-physical. Electric field, non-physical. Not made out of anything. Einstein clearly is indicating he'd like to make it out of photons.
Right. Before I forget,
Not virtual photons, but real ones.
I should mention to you, you have probably heard that Einstein was very unhappy with quantum mechanics. And yet, if you look at the history, he made enormous contributions to quantum mechanics.
And understand, though, he made enormous contributions to the idea of quantizing energy. So the quantum part, Einstein was all for. The idea that there's a little elemental bit that's the game player. Now, the fact that he couldn't see that for gravity, you know, the fact that, and I mean, he was a duplicitous hypocrite in the sense that, yes, he found it acceptable to have a complete wooey abstract energy source for gravity, but he didn't like wooey abstract energy source for electricity and magnetism. And that's a hypocrisy I can't see past. I don't know how he could get away with, I don't know how his brain didn't just explode from that hypocrisy.
Even Planck didn't have the courage to stand behind the photons that were implied in his own formula. Einstein took it to be very real and pursued it. So when you say he doesn't like quantum mechanics, it's not that he couldn't do the problem sets. It's that he had problems with the problems. Okay.
Yeah, you're just trying to say, well, you could almost mock bent space by saying, oh, you're going to measure gravity by, using gravity as the ruler. I mean, the bent fabric thing is just such a bad analogy because it needs gravity to mean anything. The metaphor doesn't mean anything without gravity doing the work.
He did not like the probabilistic nature of quantum mechanics, but he had no trouble divining what was going on.
God doesn't play dice. That's where that comes in. And yes, and I think it's rational for anybody to say, why would you like the probabilistic? Why would that be an acceptable answer to just say, shut up and calculate, and if you don't like it, tough. These are Feynman's kind of words. Why would anybody find that acceptable? That's not science.
So it's quite different. It's like saying, I don't like that joke. Well, there are two reasons. Some guys don't get it and they don't like it. Some guys get it and don't think it's funny. So this was like Einstein. Certainly understood all the complexities of quantum mechanics. He said he has spent more time on quantum, much more than on either the special or the general theory of relativity, because he said that was a real problem. That's a problem I couldn't crack. Now it turns out...
So he didn't crack either one. I'm just saying bent space is really just saying nothing. I mean, that is just the most vacuous answer. You could just, it's just saying I have an unaccountable force that doesn't do anything except create one phenomenon and can have no side effects because it's not made out of anything real. It's made out of some mathematical equation, okay? It's not made out of anything real. So, yeah, I don't have to account for any side effects. I mean, it's such a cop-out. It might as well just be an invisible man theory.
Even till the end.
Angels. Pushing.
Didn't find an answer that was satisfactory to him. The answer I'm giving you certainly works, makes all the predictions, never said anything wrong, and until...
Yeah, it does say plenty wrong. It doesn't make all the predictions. It doesn't even get all the right answers. So the Young analysis didn't even get the right answer for the double slit because the measurement problem. If you took the center of the slits to be the distance, you're not going to get mathematically correct answer. Okay, just a fact. And if you take the outside dimension of the two slits, that is the two furthest slit distances, then you're obviously conceding, the other surfaces don't matter somehow because I've made them so close to the other thing. So obviously Young did it with infinitesimally small. So what he basically did was you have a slit. He took the surface and moved it so close that this is one surface now. It's one point. There's no line I can draw from the 2 points that could be a wavelength of difference because I've put the 2 points so close to each other. There can't be any constructive or destructive. So all I've done is taken a 2 slit and changed it into a 1 slit, right? So if I make the 2 slits really narrow, I've just created 2 point sources. That's Young's analysis. Young's analysis was a single slit experiment because he made the point sources so close. If he just did this, and I'm sure he did, and he just didn't like what he got as a result, it gets much more complicated because now you have 2 patterns, you have the envelope pattern, and clearly these 2 new distances are the ones in control. This distance and this distance don't matter anymore. This distance between these 2 and this distance, those are the ones that are in control. Now anyway, we've already done that whole part.
Something better comes to replace it, we will keep using it. Anyway, going back.
I mean, that's not true. So none of these people are interested in re-examining any of these foundations. And, that's just a tragic truth. They're all very comfortable with a bunch of woo physics. The tiniest amounts of evidence possible for the biggest and grandest, giganticest theories. So they make a gigantic theory out of a shred of seems like.
The second experiment that confirmed the reality of photons. See, if you say light is made of particles and each one has an energy and momentum, do you understand why the photoelectric effect is a good test? It agrees with that picture. See, individual particles come, some have the energy to liberate it, the electron, and some don't. And if individually they cannot do it, doesn't matter how many you send. Now, you may have thought of one scenario in which all these tiny little kids can get something lifted out of the well. How will they do that?
They work together, he says, right? So what did you think they were going to do before? Of course they're going to work together. But anyway, so now we're just back to these. Just going to make he's just going to qualify the statement by saying, well, okay, if you send enough intensity, you will force some electrons out.
Maybe 10 kids together, like ants, can lift the thing out. So if you had 10 photons, which can collectively excite the electron, it can happen, but in those days, they didn't have light whose intensity was enough to send enough of these photons. But nowadays, if you use, it turns out that if you really, really crank up the intensity, you can make electrons come out, even below the frequency. That's because more than one photon is involved in ejecting the electron. So,
right, so that's just this overlap argument. You're just creating a circumstance where you're defeating the dampening because you're increasing the frequency of the light by incidentally having two low-frequency photons hit exactly the same location.
luckily, we didn't have that intensity then, so we got the picture of the photons right.
So he says they're so far wrong, and they talk. We got a great picture. It's a terrible picture, and it's made out of a bunch of canards. A bunch of statements where they say we did an experiment they didn't really do with detectors and all that kind of crap.
Anyway, Compton said the following thing. It turns out that if you have an electron here and you send a beam of light, it scatters off the electron and comes off in some direction at an angle theta relative to the original direction. The wavelength here changes by an amount delta lambda.
All right, so this is the part where I did a whole spiel, and it's just unfortunate I have to redo it all. So I'll redo it all. Shit. All right, so this is the it's also really, sorry. The difference, understanding it's not a whole photon that's doing any of this stuff. So a whole photon can't hit an electron. It's only the pieces that ever do any of this stuff. So you can have two kinds of scatter. Scatter where the bits interact and remain coherent to their original path. The energy keeps going the same way. And so you can have an image that way because you've retained coherency. The relationship between the photons is staying the same. You're bending them all the same amount, or you're doing something else to maintain their position. Or scatter, where frankly you're breaking the photons and you're just remaking them again. So fringes won't have image data, things like that, because the fact is that it could be a photon from over here, it could be a photon from different locations can make the image, the photon. So the origin has been lost when you scatter in some ways versus other ways. So the simple principle is, come on, keep working just for a little while. All right, so the photon, the little piece. So we're just talking about we have a photon that's more than one piece. And what we're really saying is that one piece is going to hit this electron. The other pieces are just going to go on their way. And so the scatter is basically saying, okay, you have a piece of this photon. It's going to hit an electron, and the electron's going to move. Now, if the electron already has a momentum, you have to combine its momentum with the bit's momentum, and you'll get some new momentum for the electron. And now it's just this pushing effect. The electron's going to move into the field. Going the opposite way, it's sending a no. Okay, so the electron's going to move this way. It's sending basically no reflection this way. So let's say it's going half the speed of light. You could sort of understand fewer things are going to reflect off of it going this way. So it's now sending basically no reflections, no reflections. And this way it's sending more reflection, more reflection. So it's compressing the energy this way, relaxing it this way. So it's sending the off part of a photon this way. This is the off part. And it's sending the on part this way. Now if it was going the speed of light, you could say, yeah, it was a clear on and off, because there'll be no reflections here, and all reflections here will be captured. But obviously it's some high percentage of off and high percentage of on. But anyway, the point is now the little bit moving this, is going to be reflecting off of this that way. So you've scattered one of the pieces in that direction. So that's the diffusion. So if you have a diffusion material, it's basically saying to the photons, I'm going to break you into a million little pieces, and then I'm going to send all the light to the other surface. And you're basically just saying on the other surface, if you have enough of these photon events happening, you can have one scattered over here and one scattered over here, and they'll hit at the right frequency and create a photon. But it's all diffused. You lost what happened originally. And the other part of this is that if it happens straight, then if the electron moves in the same direction as the energy, the new momentum, well, then you're okay. All you're going to do is degrade the frequency. So all you're going to do is slow it down a little bit. So instead of being dot, 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 you're going to have dot, dot, dot. You know, there's going to be a separation. And now that slower photon is going to have to meet up with another slower another quantum bit that's going slower to reconstruct, because now you've changed the phase of the light. So the more you change the frequency, the more you change the phase. Duh. But anyway, so the Compton scattering is just about the fact that, in its simplest form, is the more momentum the electron adds, the more change in direction, the more you're going to end up changing the frequency, because it's going to be more motion by the electron. And the electron's moving slower than the force, and that's what's creating the redshift. So you end up basically, Compton scattering basically says you're just going to redshift. So you have a frequency of light going in. After it's done scattering, it's going to be a little bit bigger frequency, the wider frequency. Because you've slowed down, you've created a process that uses time up to recreate the event. So the recreation process takes a little time, the breaking, and that creates this little bit of redshift. Now, why they don't use this explanation of redshift to explain the cosmological redshift, because it's a good explanation. We know there's hydrogen atoms in space, low density of them, but they are there. And the fact is that the photon traveling 1 billion light years is obviously going to have plenty of opportunity to hit some of those hydrogen atoms and have its frequency stretched. And that would explain why there's redshift in space. The more space you have to travel through, the more likelihood of hitting hydrogen atoms, and the more likely that your frequency has been relaxed. So anyway, but that's so the scattering obviously does indicate that waves are really going to have a hard time explaining that whole interaction. And the fact that it is very pool ball-y, that is, the momentum of the electron will be added to the momentum, the direction of the energy you're putting in with the little photon bit. There will be a simple Newtonian momentum equation, and your new direction is going to be dictated by what motion you have in the molecule you're hitting. So in the classic example of Compton scattering, you take a material, a substance, that, you know, smoke or something, and then you shoot a bunch of photons through the smoke, and what you're basically doing is now you have atoms moving in all directions. So you get a huge amount of diffusion. That is, you won't be able to say, if you shoot an image of Donald Duck into it, you're not going to get Donald Duck out. No chance. The new photons you get are going to be so unrelated, in the sense that the pieces are going to be sent from all kinds of directions, that any image data will be lost entirely. So that's why fog, you can't see in fog. It's because it's basically just taken the image and it's completely distorted it. I mean, it's sent it's broken the pieces, and now it's sending a whole bunch of pieces, but they're all broken. They're all broken from their destination, their original destination. This piece is, you know, for every pixel on your eye, a piece of the photon comes from here, a piece comes from over here, and a piece is going to come from over here. They're not going to come from here in a straight line, you know, dot, dot, dot. No, it's going to be dot from over here, dot from over here, and dot from down here. And so there's not going to be any coherent information about direction. And you won't be putting any images back together. All right. I think my first effort explaining that was probably better, but who cares? Move on.
Delta lambda happens to be 2 pi h bar over mc times 1 minus cosine theta.
So all that you don't need. All you really need to know is its momentum in. The electron already has its own momentum. You just combine the momentums, you get a new vector. That's the new vector for the quanta of energy that was part of your photon.
Are you with me? You send light in at a known wavelength. It scatters off the electron and comes at an angle theta, no longer preserving its wavelength, having a different wavelength. And the shift in the wavelength is connected to the angle of scattering.
So the more you scatter it, that is, the more the electron has changed the direction, obviously the more in control the electron is, the more, the wider your frequency is going to get.
For example, if theta is 0, delta lambda is 0 in the forward direction. If
The wider the wavelength, sorry.
it bounces right back, where cos theta is -1, this number is 2, and you get a huge delta lambda. And you can find the lambda of it by putting a diffraction grating.
So obviously the coming back part just means the electron's moving in the exact opposite direction of the photon. So you're going to get a closing of the frequency in the opposite direction.
Now,
obviously it's almost an infinite frequency in the direction you want to go. The direction you want to go is getting the effect of the electron sending an off signal. So you're going to get a very wide increase in the frequency because you got to wait for another bit to hit from the forward direction before another bit can go in the opposite direction.
what one could show is that if you took this to be made of particles,
Well, maybe what I just said is incorrect. So, some of this, it's an awful lot of, these are a lot of subtle details. You really have to keep track of them all. So, sorry. I just thought of how electrons, actually are being motivated. And so if you think about how electrons, if you think of the universe the electron is in, okay, then you can understand how the Compton scattering effect will be nothing if the electron is moving in the opposite direction. So if the electron is moving towards the photon coming in, the source photon, the little bit is here, right? So I have this is the photon. The photon is really saying these pieces are free. They're going to be fine. This piece is in big trouble. So this piece hits the electron. The electron's moving this way, which means it's already captured energy in this direction. So these little bits, it's already captured this force. So that's why it's moving. It's because it's captured a force. So when this bit hits, it's going to reflect because it's going in the opposite direction, the electron. And this last little bit is going to go in that direction. So this would be the least. This effect would be no change in the frequency because this reflection will happen almost instantaneous to this impact. So you're not going to lengthen the frequency because this bit will basically take this bit's place. This one bounces off, this one releases that energy. So it's just saying if I hit two pieces of force against each other, if that were possible, you could understand that they would hit and one would go this way and one would go that way, and you can't tell the difference. Can't tell the difference between them missing each other. You have one going this way and you have one going that way. Missing each other is going to look exactly like directly hitting each other with elastic interactions. Alright, so should throw that in. Alright, continuing.
and each particle has an energy, h bar omega, and each particle has a momentum, h bar k, and that collides with an electron, then you just balance.
So there's no point in talking about energy and momentum, right? I mean, come on. Energy is made. Kinetic energy is made out of momentum. MV is the only real part. All the rest is just mathematical abstraction. So anytime you talk about a momentum, you're already talking about a kinetic energy in the sense you could just say, okay, I'm talking about the 1/2 and the square part. I'll add that later. What's the difference? The momentum is kinetic energy. Kinetic energy can't be a something without the MV. The MV is the real part. So you could always just say momentum. You don't need to say kinetic energy.
Energy conservation and momentum conservation. In any collision, energy and momentum before equal energy and momentum after.
Alright, so that's just nonsense. It can't possibly happen when the two objects have different masses.
Sure. You set them equal and you fiddle around, you can find the new
Momentum is always conserved. Kinetic energy is not.
momentum after scattering. From the new momentum, you can extract the new weight.
I mean, it's just silly that they say this crap when they have that simple. I mean, you can't get a simpler experiment, right? You got a 5-ton train moving along. You merely drop another 5 tons on it. All right, now you have a 10-ton train going half the velocity, and you lost half the kinetic energy. You didn't lose any momentum, but you lost half the kinetic energy. It's just a fact. You still have all the momentum, and you lost half the kinetic energy. I mean, clearly, you can't conserve both. It's just silly talk.
Wavelength, and you will find this formula actually works. So I did that in Physics 200, I think. So you can, if you want, you can go look at that, or maybe it was done for you, but I don't know. But Compton scattering, the scattering due to Compton, can be completely understood if you think of the incoming beam of light as made up of particles with that momentum and that energy.
Well, the only way you can understand it, frankly, is waves would get implausible and nonsensical because it is so discrete. I mean, the electron is discretely small, and obviously you're making it change its direction without affecting all the other stuff that the wave would be affecting. It'd be affecting all the electrons. I mean, one wave. You can't make it into. I mean, it does have a vector coherency. You can't get around.
In other words, you're always going to go back and forth. Light will be characterized by a wavelength and by a momentum. It'll be characterized by a frequency and by an energy. When you think about the particles, you think of the energy and momentum.
What the hell am I doing?
You think of frequency.
Yeah, no, news flash to me. I don't know.
This was another. This is what really
There we
made after
go.
this. You could not doubt the reality of the photons. Okay. Now
So just making one of the other arguments that this all confirms. And again, and why, though, they don't recognize that Compton scattering could be a very good explanation for galactic redshift. I mean, it's a very good tired light explanation. It explains why the frequencies are red shifting, because scatter uses up the speed. It uses some time, and the time changes the frequency.
I go back to my old story. So let's remember what it is. The shock is that light, which we were willing to believe was waves, because Young had done the interference experiment, is actually made up of particles.
So, I mean, the Young experiment is completely wrong. Again, he had a two-slit experiment, basically turned into a single-slit experiment. That was his analysis. And what was the single slit made out of? It was made out of the distance between these two. This distance, not this outside distance. The only thing that's going to get the right answer is this outside distance, this one, not this one.
That's the first thing. So who needs the wave? If you send a single photon into a double slit, we don't know what it will do. We can only give the odds.
So again, more nonsense. So if you take the photons and aim them, so we have these lasers now that are very pinpoint, very small. They don't spread much, blah, blah, blah. Aim it through a slit and you won't get any fringe pattern. Aim it near one surface, you won't get any fringe pattern because it has to hit both surfaces. So, I mean, you know, all of this can be dissected if they're willing to do those experiments, and they don't bother.
Find the odds. We take the photon's wavelength and we form this wave, and then we form the interference pattern, and we...
So it's all happening on the surfaces. The two slit is the four surface experiment. The one slit is the two surface experiment. The single impediment is the two surface experiment. That's the simple truth of it, and they've missed it entirely.
Find out the wherever it is high, it is very likely to come. Wherever it's low, it's very unlikely. Where it is zero, it won't come.
Does nothing to do with probabilities. Just has to do with the obvious, right? Okay, I have a big opening. Very little chance my photon is going near the surface. The smaller I make the opening, the more likelihood that I'm going to go near the surface. So obviously that's... You could argue that's a probabilistic equation, but it's just a physical equation. It's a physical impossibility that if I make the hole small enough, the only thing that can go through the hole is something that goes by the surface. And the bigger I make the opening, the lower and lower the probability of being near the surface.
So to test this theory, it's not enough to send one photon. I mean, one photon may come here. That doesn't show you anything. You got to send millions of photons, because if a prediction is probabilistic, to test it, you got to do many times. If I give you a coin and I tell you it's a fair coin, I toss it a couple of times and I get one head and one tail, it doesn't mean anything. You want to toss it 500,000 times and see if roughly half the time it's heads and half the time it's tails.
Well, obviously in this case you want to do it with a single photon. So again, and that experiment never been done correctly. Veritasium basically proved, you know, that you can't do it. That when he did the experiment over a 5-hour period, that is, he's trying to have as few photons. He has 1 million photons that he's going to use in the experiment. When he has the 1 million photons happen over a 5-hour period, nothing, he doesn't get any pattern, nothing happens. So it doesn't work because there aren't 2 photons in the experiment at the same time. And so he had to take it from 5 hours to make it into 5 minutes. So now he had to shove the 1 million photons into the experiment in 5 minutes instead to get it to work. And what's that obviously saying? Well, it's saying obviously that, oh, well, now you do have enough photons where you can hit both surfaces. when you did the experiment right, there just weren't enough photons. Two photons couldn't hit both surfaces. I mean, you didn't have one photon hit this surface and one photon hit this surface. So you didn't get any fringe pattern. Because you didn't break any photons, you didn't make any photons at the same time. And it has to happen at the same time. So that's all you did is, it's so obvious.
That's when a probabilistic theory is verified, not verified by individuals. And insurance companies are always drawing pictures of when I'm going to die. They got some plot, and that's my average chance. And I don't know when I will be part of that statistic, because in fact, it usually looks like this. Life expectancy of people looks like that, but doesn't mean everybody dies at one day. People are dying left and right, so there's probability on either side. So to verify this table that companies have got, you have to watch a huge population.
I think it's much more slanted than that, actually. I mean, the slope up is very gradual. The slope on the other side is very, you're in big trouble. Once you hit 90, it's 50-50. Every year you're rolling 50-50. There's a 50% chance you won't be there the next year. I mean, those are tough odds to beat year after year, right? I mean, my parents made it to 95, 96. So for 6 years, they rolled those dice and it kept going odd, 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 odd. But they knew the heads, the tails were, they got heads. But,
Then you can do the histogram and then you get the profile. So whenever you do statistical theories, you got to run it many times. I'll tell you more about statistics and quantum mechanics. It's different from statistics and classical mechanics, and we'll come to that later.
Oh, who cares? Blah, blah, blah. Shouldn't, this part's a little boring. Let's see. Well, we're almost at an hour. Let's just see.
But for now, you must understand the peculiar behavior of photons. They're not particles entirely. They're not waves entirely. They're particles in the sense they're localized energy and momentum, but they don't travel like Newtonian particles.
And so he says,
They were Newtonian.
obviously, they have momentum, yet they don't travel. What sense does it make, right? With the velocities in the momentum, I mean, what do you mean? They don't travel. I mean, obviously they do. They are moving through three-dimensional space. They do have a velocity, and they do have a mass. And it's because you don't understand why they have a thing called energy, why they make an effect. So the simple thing they have wrong is they're not understanding that the ultraviolet photon, the pieces, don't have more momentum. They're just going to apply their momentum over a shorter period of time. And applying the momentum over a shorter period of time increases the efficiency with which you get the momentum to stay in the object. Because the object is going to dampen the energy. So if you can defeat the dampening, you'll get more of your energy into the system. And it's that simple. And they've missed it. And that's just a fact. And they're just going to keep preaching this really bad version of evolution. This is like the version of evolution where they say the giraffe wanted to be, it was trying to reach higher leaves, and that's why somehow its sperm changed, because it was reaching, and the sperm knows it wants a bigger neck next time. It doesn't work that way. It doesn't work the way they're saying.
The particles, you'll never understand why opening a second slit reduce the amount of light coming.
So that doesn't happen. So that's the fake experiment. He's going to talk about electron experiments that are really, didn't happen either. I don't know if I want to do a part 4, but maybe I will. But we're probably far enough along, because I think now he's just going to start talking about electrons.
Somewhere. All right, so this is the story. So now comes
de Broglie.
Physicist, de Broglie.
All right, de Broglie, whatever. And this is where it just gets nonsensical, because photon particles are acting like a wave. Therefore, we have to believe that anything that is a particle is waving. And no, we don't. But anyway, so enough of a video, I think. Too bad about the fact that I did it twice. And yeah, second version just wasn't quite as good. But anyway, it'll have to do. So till the next time, and such and so forth and whatnot.